So last time we learned about light and how light and matter interact, and today we'll finish our discussion on light by talking about spectra and what we can learn about objects in space by studying their spectra. So to review, light is a form of energy. It's an electromagnetic wave, and so you can think about it as a wave or as a particle called a photon. And different energies of light can behave in different ways, going from the longest wavelength or lowest energy radio waves up to the highest energy or shortest wavelength, which are gamma rays. Matter is the stuff in the universe that's made out of atoms, and atoms are made of protons, neutrons, and electrons. And matter can emit light, it can absorb light, light can pass through matter, or it can reflect or scatter off of matter. And the way that light and matter interact basically governs all the stuff that we see with our eyes. So which of the following will determine the energy of a photon? So we can pick multiple choices. So, wavelength and frequency are the two that will affect the energy of the photon. Brightness will be more of a factor of how many photons are coming from that object, but all the photons will have the same energy. And the speed of light is a constant, so whether that's a gamma ray or a radio wave, they'll all have the same speed. We've covered the basics of light, and now what else can we learn by studying the light coming from space? So we'll talk about three basic types of spectra. We'll use that understanding to describe how we can study what elements are in the matter that's emitting or absorbing that light. We'll talk about the temperatures that we can determine by studying spectra, and then we'll talk about how studying spectra can tell us how things are moving. So we saw this graph last time. This is a black body spectrum for objects at different temperatures. So the curve is the spectrum, and so at each different wavelength, so wavelength is the x-axis, there's a different intensity or number of photons coming from that object. So for a very high temperature star, it's emitting a lot of photons at all wavelengths, but it emits the most photons at this peak wavelength, which is somewhere in the ultraviolet. And where this peak occurs is governed by Wien's law that we saw last time. Then for a lower temperature star like the sun, its peak wavelength is occurring in the ultraviolet, but it's still emitting light over this whole range of wavelengths. And then even something that has a very low temperature, like a human, still emits some light in infrared wavelengths. So the big takeaway from this graph is that the higher the temperature, you're going to emit more light over all wavelengths, and then the higher your temperature, the more energy the photons that you emit are going to have. So because this is at a shorter wavelength, that means the photons it's emitting are higher energy. So I said those curves on the previous slide were black body curves. So what is a black body? So a black body is an object where all the light that is incident on that object is absorbed, and then it will emit its own radiation. So examples of black bodies in space are things like a star, and then for a more terrestrial example, the oven in your kitchen is a black body. So there's some heating element in your oven that emits radiation, and then the walls of your oven are constructed in such a way that it doesn't let that heat escape. It traps all that energy in and cooks your food. So black bodies, we understand the physics of black bodies very well, and so it's useful to think of anything we can imagine as a black body. So physicists and astronomers will approximate everything as a black body just because we understand the physics of black bodies really well. So things like planets are not black bodies, but if we model them as a black body, then we can say some things about their spectra that we expect to see from them. So planets are not black bodies because they don't absorb all the light that hits them. They reflect some of that light. We'll come back to that in a little bit. So what are the different types of spectra that you can observe? So there's 3 different types. And we will see all of these in an astronomical point of view. And things that we see in space are usually a combination of all of these 3 things. So there are emission spectra, there's a continuous spectrum, and then you can have an absorption spectrum. So a continuous spectrum will be, like we saw with the black body curves, just a line, and that's telling you that at all of these different colors, this object is emitting that kind of light. An emission spectrum is a line that's going above the continuous spectrum, and so there's extra photons being emitted at these wavelengths above the continuous spectrum. And then the absorption spectrum is a gap in the continuous spectrum. So something is causing what would be a continuous spectrum to basically lose photons. So those photons are being absorbed by something instead of traveling to your detector. So the 3 spectrum, you have continuous spectrum, which is the smooth rainbow of light through different wavelengths that have different intensities. And the continuous spectrum is going to be coming from a black body. Emission line spectrum are only specific wavelengths, and they are produced by low density but very hot gas. And then absorption spectrum are also from usually a gas, but it could be some other material that's in between you and the source of the continuous spectrum, and that gas is absorbing some of the light from the continuous spectrum. And so these will be dark lines or dips in your continuous spectrum. So we'll see how we can produce these different spectra. So a continuous spectrum, you just have to have some hot light source. So in this example, it's an old light bulb that produces light from a filament, could be a star. You put that light through a prism that splits the light into its continuous spectrum, and you can see it's emitting light at all different wavelengths or all different colors. And if you were to plot the spectrum in terms of its wavelength and intensity, it might look something like this, where the light appears yellow to our eyes because it's emitting the most light in the yellow region, and it's emitting less light in the red or the purple side of the spectrum. If we take, instead of a light bulb emitting gas, and we just have a cloud of warm gas, it can also emit light, but when it emits light, it won't be in a continuous spectrum, it will have an emission line spectrum. So instead of the whole rainbow being represented, it will just be very specific colors that correspond to very specific wavelengths of photons being emitted. An absorption line spectrum can be produced if we put our continuous source spectrum and pass the light through a cold cloud of gas. So the continuous spectrum that we expect to see is still there, but there's gaps missing in our continuous spectrum. So these are the black lines of the absorption spectrum. And if we plot that intensity and wavelength graph, then we'll still see our continuous curve, but there's dips that correspond to the wavelengths where the light was absorbed. So what does a real-life spectrum look like? So this is the spectrum of the sun. So you can see it's mostly a continuous spectrum with colors all across the rainbow, from red, orange, yellow, green, blue, indigo, violet, but there are some gaps missing. So that's telling us that there's some gas around the sun that is absorbing some of the light. And so these lines are the absorption lines from the sun's atmosphere. And by studying where these lines occur, we can study what the sun is made out of. The way that we do that is a consequence of physics and quantum mechanics. But each chemical element will have different wavelengths of light that it emits depending on the transition of electrons in various orbital levels. So level 1 is called the ground state energy. So this is where the electrons in that atom want to live. So these are specifically for hydrogen. So if we look at hydrogen on the periodic table, it has an atomic number of 1, so it has 1 proton and 1 electron for a neutral hydrogen. That photon wants to live in level 1 of this diagram, but through some mechanism that we'll talk about later, that electron can be moved up to different energy levels, and depending on what energy level the electron starts at and the energy level that it ends up at, it will emit a photon of a specific wavelength. So, for example, a photon going from the second level of hydrogen to the first level will emit a photon that has a wavelength of 121.6 nanometers. So now when you see a spectrum and you see an emission line at this specific wavelength, then you know that there was hydrogen gas there, and that hydrogen gas had an electron transition from the second energy level down to the ground state energy level. And so you build up this knowledge of these different wavelengths for all of the elements on the periodic table. So you might be wondering now, how do I get an electron to one of these higher energy level states if it wants to be at ground level? So the way that you do that is the opposite of what we just talked about. So if a photon that has 121.6 nanometers interacts with this hydrogen atom, the atom will absorb that wavelength of light and go from the first energy level up to the second energy level in that hydrogen atom. If it was 121.7 nanometers, then it wouldn't be able to do this transition, and that photon would either pass through the atom or scatter off of the atom, but it will not. It has to be this precise wavelength in order for this transition to occur. And so these, so the downward transitions produce an emission, so that's a photon being emitted, and that wavelength of the photon is correlated, you can correlate that to a color. So the different colors that we see are light that has different wavelengths. So for example, this 486.1 nanometer line, which is kind of blue, is the transition from the fourth energy level to the second energy level in the hydrogen atom. And then for the absorption spectrum, you have to have a cloud of gas, of hydrogen gas, in between your light source and the observer, and then the observer can detect, say, for example, if there's a gap in the spectrum at 656.3 nanometers, then that means that there was a transition, a photon was absorbed in that hydrogen gas that caused a transition from the second energy level up to the third energy level. And like I said, each element will have its own spectrum associated with it. So and these are just the visible spectrum. You can get transitions and absorptions and emissions in the other regions of the electromagnetic spectrum, but we're humans and we see invisible, so we'll just stick with what we can see in visible light. So helium has some emission, a little bit of red, a little bit of kind of orange, and then green and blue. Sodium just has a doublet in kind of a yellow. Neon is just red, orange, and yellow, and no green or blue. And these specific wavelengths, if we see that transition, then we can say that cloud of gas has neon in it. It can get more complicated because when we went over the hydrogen example, we were talking about a neutral atom. So that was one electron and one proton, so the electric charge canceled out. But atoms can be positively charged or negatively charged. So let's say we're talking about helium, that shows up a lot here, or I guess oxygen and neon are the ones that are charged. So if I look at oxygen, it has 8 protons and 8 electrons. If I lose one of those electrons, then I can be positively charged, so that would be the O+, or I can gain an extra electron, and then I would be negatively charged. So if the atom is positively or negatively charged, then its spectrum will also change. And so this neon is actually doubly ionized, so it's lost 2 electrons, so it has a positive charge of 2. So you have to pay attention not just to the chemical element, but also what charge it has. And so in this picture, you can see there's different helium lines. There's that oxygen doublet, and then there's a neon line, a neon ++ line. And it can get yet more complicated still because it's not just atoms that we have to think about, but molecules as well. So molecules, which could be hydrogen, 2 hydrogen and 1 oxygen to make water, that's going to have a different emission spectrum than hydrogen or oxygen did separately. So you have to do a lot of chemistry basically to understand these absorption and emission lines, but once you do, you can apply that to what you see coming, the light that you see coming from space, and use that to study, for example, what stars are made out of, or what the atmospheres of planets are made out of. So again, this is the solar spectrum, and these black lines are the absorption lines from the atmosphere of the sun, and so by studying where these lines occur, we can study what elements make up the atmosphere of the sun and therefore probably make up the rest of the sun as well. Okay, so just as a class, we'll do some practice for these. So so we have these letters A, B, C, D, and E. So which letters correspond to absorption lines? You can just shout them out. Yeah, so D is one of them, and C. Yeah, so anywhere it goes below the continuous spectrum is an absorption line. And then, let's see, so this says which letters label the peak or greatest intensity of infrared light. Yeah, it'll be D or E. So infrared is the right-hand side, and that's the highest part that is in the infrared. So which labels are for emission lines? So it'll be A. So A is above the continuous spectrum, but B and D are, or C and D are below. So just A for the emission. So we talked a little bit about this last time, but now that we have a little bit more understanding of what a spectrum is, we'll come back to how we can study the temperature of something based on just the light that we receive from that object. So for the fireplace poker, the hotter it gets, it changes color, and the hottest color it's emitting, it looks white, and that's because it's emitting light over all visible wavelengths. So white light that you see is equal parts red through violet that your eye is detecting. Anything that has a temperature is going to emit light, and if we want to make the assumption that the object is a black body, it needs to be a dense object, meaning like a solid. So if it's a hot object but it's a gas, then it's going to have an emission spectrum. But if it's a hot object that's dense, like a planet, then we can assume it's a black body. And its spectrum will only depend on its temperature. So when we look at these black body curves, one of the ways that you can determine what temperature the object is make your spectrum, so you plot one of these curved lines, and then wherever the peak occurs, you can use Wien's law to calculate what temperature that object has to have. So when you do that for the sun, you get this temperature of 5800 Kelvin, and that's the temperature of the surface of the sun. When we learn about stars later in the semester, we'll talk about the temperature of the inside of stars and the structure of a star. And then you can do the same for objects that have really low temperatures, like human emitting infrared light, but also planets will emit light in the infrared as well. So they don't do nuclear reactions, so they're not emitting light over the whole wavelength range, but they do have some temperature associated with them, and so they will emit some amount of photons. So if humans have a temperature and they emit light, why don't we glow in the dark? Yeah, so if our eyes detected infrared wavelengths, then we would be able to see people glowing in the dark. So that's kind of a trick question. Humans do glow in the dark, it's just in the infrared wavelengths, which our eyes can't detect. But there are animals that have adapted to see in the dark, and so they can detect infrared wavelength. There's also animals that can see in ultraviolet wavelengths, which humans can't see either. Okay, so we can take a spectrum of some object out in space, and we can learn a lot about that object by studying the spectrum. So what is this object? This is a real spectrum of an object out in space. The continuous spectrum looks like the solar spectrum, but some of the light that should be there has been absorbed by the object. So this continuous spectrum in the visible wavelength light is reflected sunlight. However, not all of the light got reflected, only the more red colors got reflected. And so this object, if you look at it with your naked eye, is going to appear red. Then its actual black body curve is the curve to the right. And so by figuring out where that peak in its black body spectrum is, we can calculate its temperature using Wien's law, and it turns out that this is about 225 Kelvin. So room temperature in Kelvin this is much lower than room temperature, basically. The absorption features are from carbon dioxide, so that's telling us that whatever this object is has a cloud of gas around it, so it probably has an atmosphere, and in that atmosphere there is carbon dioxide. And then there's also these emission features, and so in that atmosphere there also has to be some kind of hot gas that's able to emit these ultraviolet photons. So what is this object? It turns out that this is the spectrum of Mars. So remember, none of the planets in the solar system emit their own visible wavelength light. So if you are looking at a telescope and you see it with your eye, you're seeing reflected sunlight. So this part of the center part of the curve is basically the solar spectrum, and then because Mars is red, the red part of the solar spectrum is is bouncing off the surface and coming back towards the Earth, but the bluer photons are being absorbed by the planet. Then Mars has an atmosphere that has carbon dioxide in it, and it has a pretty low temperature, so its black body curve is shifted way over into the infrared. Okay. And we saw this last time too, but now again that we understand spectrum, we'll talk about the Doppler shift. So if we think about the Doppler shift for sound, when the train is not moving and it sounds its horn, the person on the right and on the left would agree that the pitch of the horn sounds the same. But now if the train is moving towards the person on the right, they're going to hear the train horn at a higher pitch, and the person that's to the left, where the train is moving away from them, they will hear the horn at a lower pitch or longer wavelength. And the same thing happens for light. If you have a light source moving towards you, the photons will be blue shifted, or their wavelength will be shorter. And if the object is moving away from you, then the wavelengths will be red shifted or longer. So we have this example of the Doppler shift for sound. A very clear shift in the pitch, meaning clear shift in the wavelength when you go from the train or the siren moving towards you versus moving away from you. And light, because it's also a wave, behaves similarly. So object moving towards you, its spectrum will be blue shifted. So all those lines that you studied in the lab about hydrogen, and you said hydrogen has this very specific wavelength. Now if I take that hydrogen and I start moving it towards you or away from you, now those lines are going to be shifted. So moving towards you, blue shifted, or moving away from you, red shifted. And so for things in space, you really need to look at the whole spectrum as a whole to see how it's red shifted or blue shifted, to say what elements they even are and if it's moving towards you or away from you. And then if the object is moving perpendicular, so just across your field of view, then it's not going to be red shifted or blue shifted. So here's an example. So we have the wavelengths for some material that you measure in the lab, and this is what it looks like when it's stationary. So you've got a blue, a green, and a red, let's say, emission line. Now if I take that object and I start moving it away from you and have it emit, now its red light is going to be shifted even more red. That green is becoming a little yellow, and the blue is shifted more towards, it's not as blue anymore. Do it even faster. Now the red is even more red. Now the green light is completely yellow, and the blue line is starting to look more green. And then you can do it the other way too. If we have the object move towards us, that red line starts to look more orange. The blue line, or the green line, is starting to look more blue, and then the blue line will start to look more violet. So by studying the spectrum, you can figure out what it's made out of, but you can also tell whether the object is moving towards you or away from you. So let's say you observed a star and you measured its Doppler shift. Does that mean you know the exact velocity that it's moving with? Not necessarily. So if you look at star 1, if it's moving, just all of its motion is in a line with the Earth and it's moving away from us, then whatever Doppler shift you calculated will tell you how fast that object is moving. For star 2, because it's not moving towards or away from us, it's just moving perpendicular, we're not going to measure any Doppler shift, but that star still has some velocity. So we're not able to measure its velocity because it's moving perpendicular. So basically, we could only say for star 2 that it's either stationary or moving perpendicular to our field of view. But we can't tell exactly which one, just with one measurement. And then for star 3, this one's moving kind of across our field of view, but also slightly away from us. So we'll measure a Doppler shift, but that would only measure the velocity away from us. We can't measure the velocity that's perpendicular. So basically the Doppler shift velocity that you measure will just be part of its velocity. You can't say what its total velocity will be. So let's say I measure an emission line in a lab at 500.7 nanometers, and then in a star, I measured that line to be 502.8 nanometers. So what can we say about the velocity of that object with respect to the Doppler shift? Yeah, so the wavelength is different, so the star has to be moving, so we can rule out stationary. And then, again, the line is different, so it's not just going to have perpendicular motion either, so we can eliminate that one. So wavelength is different is telling us that it's either moving towards us or away from us. And the wavelength is greater than what we observe in the lab, so it's redshifted, so it's moving away from us. And so we talked about how we think all of the galaxies in the universe are moving away from us, and this is how we can figure that out. We can look at the redshift of all of the galaxies and see how they're moving with respect to us. And if they're all redshifted, then they're all moving away. Okay, so what did we learn today? There's these 3 different types of spectrum, and by studying those spectrum, we can tell what atoms are, or what elements an object is made out of. And for any dense object like a planet or a star, it's going to emit some amount of photons, and what the shape of its spectrum will look like depends only on its temperature. And so if we can collect the spectrum of one of those objects, we can tell what its temperature is. And then again, if we study the spectrum of objects out in space, if the spectrum is blue shifted, that object is moving towards us, or if the spectrum is red shifted, then it's moving away from us.